Well, maybe you've been wondering what I've been up to for the last month. Maybe not. I haven't made much progress on the actual airplane, but I've been working pretty steadily on this flap actuator that I talked about in my last video. Let's go have a look. Alright, well here is the latest version. I assume it's the last version, hopefully, of this flap actuator and indicator for my Sonex. I've done quite a bit of work, obviously, with 3D modeling, with some electronics here. There's two custom-made PCBs, or printed circuit boards. One that goes behind the screen and the button here, and then another one down here on the bottom that, if you look closely, you can see that it's attached. These two boards are attached to each other through some 90-degree pins down here. Inside the board here, we've got a small buck converter, so I have 12 volts coming in through this cable here. It comes in and attaches to the motor driver back here, and then it splits off from the motor driver and comes up to these terminal pins up here, and then through the circuit board, it goes up to the power, the buck converter right here. It drops it from 12 volts down to 9 volts. Then from there it goes into the Arduino. The Arduino has its own power drop circuit in there, so it'll go from, I think it goes anywhere from 7 to 12 volts. I decided to go ahead and put 9 from there into the voltage in pin on the Arduino. And then from there it pops out to a 5-volt circuit, which is what the Arduino uses. From here it's a 5-volt circuit that goes out to these wires, out to the flap actuator, just the reading pins on that. So I'm pushing out 5 volts and a ground that goes to that, and then there's a third wire that comes back through here, which is this yellow wire. Coming off of the flap actuator. The yellow wire gives a signal somewhere between 0 volts and 5 volts, which comes all the way back up here, plugs into my Arduino with this first pin over here. Again, another terminal block. That's read by the Arduino to see exactly where the flap actuator is in its extension. So either 0, like I said, or 5 volts for fully extended. The Arduino can then take that reading, do some math against it, and then make it pop up on the screen over here to show what your flap setting is, where the actuator is sitting in its range. There's also another set of terminal blocks here that connect the switch. So I've got 3 wires coming off the switch. The center one is ground, and then I've got this kind of pink wire and this purple wire. They are, when I flip the switch one direction or the other, it sends a signal. Basically it grounds these 2 pins, which are up to 5 volts. It grounds them, which then sends a signal to the Arduino to say, hey, the pilot is doing something with the switch. And from there it does some processing. If I'm telling it to go up or down, it figures out, based on the readings that I've gotten through this yellow wire, where this flap actuator is in its range, and decides what notch, we'll call it a notch, it's sitting at. The Arduino figures that out, and then based on which direction I push the switch, whether it's retract or push it down to extend, it'll move to the next notch or the previous notch. And all of that information is carried over these wires, this kind of 8-pin connector that goes from the Arduino board here over to the motor driver board, and tells the motor driver to either extend or retract the flaps using this, again, 12 volts where we started from. So it uses the same 12 volts going in, running off the airplane power to run everything that's here, as well as the power on the actuator. Now this 3D printed part here is designed to work with a 2¼ inch panel mount hole. It fits inside of there very nicely. So there's a switch here, up and down, and then there's also a screen here to tell you where your actuator is in its range. Alright, well let me go ahead and plug this in. Got it plugged into a 12 volt power supply here coming off my wall. It's reading right now, it says flaps at the top, 0, which is correct because it's sitting at fully retracted right now. And I have it set up right now to do a 0, a 10 degree, and a 30 degree notches, so there's 3 different notches. Sonex recommends that you take off with 10 degrees and you land with full flaps extended, so using the code, I can actually change that and have several different settings in here. I think you can fit about 6 different notches. So if I go ahead and click the down button here, It extends out to 10 degrees and then stops. And these aren't actual degrees. This is just a number that I kind of put a number to. It could be 0, 1, and 3 if you wanted it. It's probably better to have a few numbers in there so that it actually extends and has some amount of movement here. I'll click it down one more time. There, and it's fully extended at that point. I've also written code in there that you can stop it at any point. Like if you wanted to go to, 20 degrees or something instead of, all the way down, you can do that. But again, in the code, you can actually put in another notch in here for 20 degrees if you wanted to. So I can click it and then stop it anywhere along the way, and it gives me a half a second of holding that button before it starts moving the opposite direction. Let me demonstrate that too. As long as I let go of it within a half a second, it'll just stop where it is and leave it as it is. This is a 3D printed part that I modeled. I decided to use the time to try and learn another CAD program. I typically use SolidWorks, and through EAA I have a reduced price version of that. I think I spend like $25 a year or something like that for a license to use it for their maker version. EAA also has another CAD program that you can get a license to, another sort of non-commercial use type one. It's called Solid Edge. It's made by Siemens. So I thought I'd use this time to teach myself another CAD program. So that's part of what took so long to get this thing working. I will say SolidWorks is definitely still my preferred CAD program. The Solid Edge one it's a little bit buggy, and just the workflow just didn't go very well as a result of things just work differently, and I had to get my brain around it. And then also it's just kind of buggy. Sometimes it would just lock up for no reason. But anyway, this is what it turned out to look like. These are actually 3 separate 3D printed parts. One of them is the faceplate here. It's just this, part that's going vertical here. And then there's a bed, what I call the bed, I guess. And inside of here, this bolts in right here in the front with 4 bolts, 2 on each side. And that kind of goes from here back to about here. And then I have the motor driver bed that sits in the back here. And so this front part is connected through these 4 screws. The rear end of this, there's 4 screws down inside of here that bolts it straight forward, and then a couple here up on the side to give it a little extra rigidity up here to keep it from, drooping or whatever. I added a couple of holes here in the side that are sort of oblong shapes so that you can use some wire ties to keep your cable management under control here. It seems to work out pretty well. And then obviously there's also a place for these fins to come down from the motor driver. I still haven't had any issues with any kind of heat coming off of this motor driver yet. It's rated for, I think it's like 36 amps or something like that. And the actual actuator here, it's rated to only use a maximum of 4 amps. I put it on an amp meter just to see what kind of draw I was getting for the whole circuit, and I was I think I saw 2.5 if I really put a lot of weight on the actuator, but really it was very well within the limits of the motor driver. I mean, stupidly so. Anyway, I haven't had any issues with it overheating in any way. In fact, I haven't felt any heat coming off of this at all. I've run it so much in testing that this motor actually started to feel warm to the touch through the case and everything, but never had any temperature change on the chips here on the motor driver. So, all right, so full on, the thing that took more time, I think, than anything else, and why it took so long to put this video out, was doing the software development for this this whole little package. It's not a terribly, advanced piece of software. I've spent a lot of time putting a lot of these comment blocks in here, that all these kind of grayish colored things that'll start with a slash star and then end with a star slash. So anything in between those is considered a comment. It's there just for people to look at. The compiler doesn't actually read that. The things that really are worth noting in this, I think, is So for example, this full retract value and full extend value, because the sensor on the Arduino, it uses an analog pin on the Arduino to read what the distance is that the actuator has moved. Basically, I think I mentioned this earlier, but you put in 5 volts positive and ground, and then it has a third wire that comes out, and depending on the distance that the actuator has traveled, it'll put anywhere between 0 and 5 volts output. The Arduino then reads that pin and assigns a number to it between 0 and 1023. So basically the process is to retract the flaps all the way, plug in the USB device on the Arduino to your computer, read and see what that value is. In my case it was 6 for the full retracted value, and then I would extend it all the way and then do the same thing and read it again. And in my case again it was, I think it was 879 or something like that, so I put it at 880. And I use sort of roundish numbers, and we'll talk about why here in a second. Because it's an analog sensor that's reading the position, that value may kind of fluctuate up and down. Even though the actuator isn't actually moving, the reading might come off and bounce around by 2, 3, 4, 5 of these values here. So what I've done is I've added an anti-flicker value here that you can put in. On mine, just doing some testing here earlier today, it looked like 4 was about the value, where even though the actuator was sitting still, it would fluctuate anywhere between, I think it was like anywhere between 876 and 880 or something like that. So I went ahead and put in an anti-flicker value of 4, and what that does is it'll round down to the nearest 4. So if it's popping up here and saying it's, let's say it was popping up saying 883, well, they would return the value of 880 instead. If it was 882, it would return 880. The calibration output's an important one. You should only have to have this turned on at the very beginning. Turn this to true, and it'll output those numbers that we talked about up here. It'll just spit out whatever the sensor is reading at any given time. Every, I think it's millisecond or whatever. It'll just come up with a list of them over and over and over and over and over. This max idle timeout, this is how long, if you were to flip the switch and then go the opposite direction, 500 milliseconds, so half a second is how long it sits before it starts to move the opposite direction again. So this target tolerance is another thing that you can play with. Basically what the target tolerance is when the actuator is in motion, sometimes it'll coast a little bit beyond where you want it to stop at. And so this is a place where you would set and say, okay, when you're getting close to hitting your next mark, stop 5 degrees before, or 5 readings before it actually gets there, so it can slow down and stop where you want it to. Again, this is one of those things you've got to test and play with on your own actuator to kind of find out what that number is. On mine, 5 was about the right number. Okay, this is kind of a cool part here. So the code is written so that you can actually add as many of these different angles or notches. This probably should be called notches instead of angles, but well, not really. This is basically where you set where each notch would stop in terms of angles. So 0 would be fully retracted, 10 would be my first notch, and 30 would be fully extended. I could go in here and put in another comma and hit 20. And what this does is on the screen it'll actually put, instead of just 10, 0, 10, and 30, now it'll say 0, 10, 20, 30. And the code's already written to make sure that it stops at each one of those as a notch. All right, so let me, I'm going to leave this with these 4 notches now. Let me go ahead and I'm going to reprogram the board really quick, and then I'll show you what the screen looks like once I've done that. And there it is. So you can see now that I've got 4 different notches now. I've just added the 20 in there. So I'm going to go ahead and raise the flaps 1 notch. Oh, actually, before I go on here, let me, I've got to unplug my USB cable and plug in my board here again. And then plug this thing back in real quick. Alright, so now so it stops at each of these notches. All I really had to do was just add an extra angle into that array called angles, and it allows me to add as many as I want. Obviously, you're going to run out of screen real estate really quickly. This, I think it only has like 128 pixels or something like that height. So the more of these numbers or notches you put in there, you're going to quickly run out of space on the screen, and they're just going to kind of overwrite each other. So 3, 4, 5. You could probably get 6 in there and be safe. I don't know. Alright, well maybe you're wondering if you can build one of these yourself based on what I've done, and the answer is yes. If you want to, you're more than welcome to. If you go to my GitHub repository, it's github.com/danderflieger. And if you go up here where it says repositories, click there, and then go to the Sonex flap control, click on that. This has a quick little readme on it and kind of tells you how it all sort of works. Probably need to go through and update this again so that there's some more information, but there's a quick parts list here, some what you might need if you're going to create your own printed circuit board, some additional ribbon cables and things like that, and other tools that you could use. Kind of goes through how the wiring goes. Some of this was, for example, this image here was actually sent to me from Sonex, telling you how to wire up the switch. Incidentally, if you wanted to not use the Arduino to control the flaps, instead of having the notches and all that stuff, if you wanted to do it where you just connect a switch, which is how their drawing shows, basically you can have it connected to do that. Just go 12 volts directly into your switch with a little cross going across it here. So basically you, well, if you look at the image you can figure it out. Basically if you push and hold the switch up, it'll retract. If you push the switch down and hold it, it'll extend until you've actually let go of the switch. I decided to do all of this because I'm not a huge fan of having to hold a switch while I'm trying to, I'm on short final or something like that. I just want to hit the switch, let go, and get back to flying the airplane and not have to worry about having my hand away from, the throttle or whatever. So that's part of what prompted me to do this. But you could do it this way as well. You can use the indicator, the little screen on the indicator, to show where the flaps are, and then just instead of wiring in the switch into the PCB, you can actually wire the actuator directly into your switch and skip using the Arduino. It'll still work. It'll still show the position just the same. There are two different circuits on the Arduino. One sends a signal for it to extend or retract, and the other one reads the current position of it. So you could interchange either one of those. Talks about all the different the motor driver locations, all the terminal pins that you need to use. Talks about what PWM is in case you're not familiar with what it is. There's a pretty good link here you probably want to read up on. It's probably better than what I explained, talking about how PWM works. And then it talks a little bit about the position sensor in the flap actuator. Feel free to read through that. It kind of tells you what wires do what, where to connect them, and kind of how the position sensor works. Lots of cool stuff. Anyway, if you're not really familiar with GitHub, basically it's an online repository where people who write software can kind of put their code up for other people to use and edit and whatever else. Basically, you can just use a terminal and go grab this Git repository and bring it down onto your computer where you can, edit it, use it to do whatever. In fact, I think I have a video out there that kind of talks through this for my angle of attack sensor. So maybe I'll put a little card in here for you guys to see it. All right, well, hopefully you found this one interesting. While it's not working on the actual airframe of the airplane, I still consider this, working on the airplane. It's been a little bit since I've actually touched metal, apart from the little faceplate that I put on the indicator there. Anyway, if you've found this video interesting, feel free to give it a good like or leave a comment. If you see something that you are concerned about or you think might not be right, feel free to leave me that comment as well. If you haven't subscribed already, consider doing so, and we'll see you on the next one. See ya.